it is a great pleasure to be speaking as an invited speaker at BIT's 5th Annual World Congress of Advanced Materials. Whereas today, my talk will be focusing on a topic concerning a model of high TC superconductors. Before I go further into my presentation, I would like to discuss the main contents or the highlights of my presentation. First of all, I'd like to discuss the recent and the upcoming applications of superconductivity. And this was somewhat shown in the previous presentations. And some of the applications which I would like to discuss is the MRI, magnetic resonance imaging, and also the newly advancements in the railway technology, along with space technology. Further, I'll also be talking about the heating sequence and also the development of bulk MgB2 and what were the processes that were used to establish this sample. Furthermore, I would like to also discuss about the design and development of a prototype of my maglev train, which I had designed to find the optimal gap between the train track and the railway. And lastly, I would like to conclude this presentation of talking about my current research that really focuses on the modeling of high TC superconductors, especially for bulk MgB2 and GD123. So mainly the question is, why MgB2 material, or what is the essence of bulk MgB2 material? Well, magnesium diboride is basically a simple ionic binary compound, which is basically known for its cheap quality, and also it is highly inexpensive among all intermetallic superconductors. It is not only lightweight, and it does not only have eco-friendly properties, but it is also known for having the highest TC among intermetallic superconductors. And over here, I have shown a multifilamentary MgB2 wire, since it's one of the current applications where it can amplify the generated amount of current, and also it can be coated around superconducting tape, since due to the very low cost of production. And I'm also showing a simple structure of MgB2, and well, this is an ionic structure where it exists in 2 electrons in Fermi level with pi bonds and the sigma bonds. And further, I'd like to discuss about the potential applications of MgB2. Well, it was discussed earlier, but magnetic resonance imaging. MgB2 had somewhat revolutionized the healthcare systems due to NMRI and MRI. Now we have the potential to be scanning the bodily processes and in the current diseases in our body. Not only healthcare system, but it had also plays a substantial role in the transportation industry, since now we have the production of maglev trains. Also, high-powered magnets can be also used for gravitational studies in the space technology. And furthermore, both MgB2 superconductors had played a great role in the energy production, since superconductors can be used in the wind power, since by using the superconducting wires, it can produce more renewable energy, such as the wind energy, and it can generate more current without any loss. So now I'd like to briefly discuss about how I prepared a sample of bulk MgB2. So the first processes that was utilized is to make the powder preparation. In order to make the powder, I needed the Mg metal and the 2V material, which are both 99.9% impurity, and the molar ratio to produce it was 1:2. And in this MgB2 sample, I had also varied the contents of silver, and the varied contents were 0%, 4%, and 10% in weight. After definite proportions of the sample was prepared, the grinding in the glove box has to be happened, and this was grinded in the condition of argon. And this is like a simple picture of where the grinding process had happened. After the grinding processes had happened, it is necessary to use the uniaxial pressing machine to create the disc shape of the sample. And lastly, it was wrapped in TA foiling, and it was sintered in argon temperature. And the atmosphere that was utilized for the sintering process was 775 degrees Celsius. And after the sample preparation, I had done some modeling analysis. Well, this is the heating sequence used for the production of MgB2. For addition, in the 6-hour periods, there was an 100 degrees increment which was increasing until 600 degrees for a 6-hour period of time. Then for 5 minutes there was a stable temperature, and again in the additional 50 minutes I had increased the temperature by 775 degrees. And then there was 3 hours of constant temperature, and lastly cooling had to be happened for 8 hours. And after these methods were taken for producing bulk MgB2, I had used squid magnetometer to analyze the superconducting performance. So this is basically the pictures of me using the squid magnetometer. Since by using this material, I was able to obtain the superconducting transition temperature for various MgB2 materials, and I have provided some data over here. For silver free, it was 37.1 Kelvin, and for 4% addition of silver, it resulted in 37.8 Kelvin, and for 10% silver addition, it ended up with 37.6 Kelvin. And this is the following graph. So therefore, this data was also it's currently at press at Acta Physica Polonica A, which I'll be discussing further. After I had performed the magnetization experimentation, I had used the Bean's critical state model to calculate the critical current density. In order to calculate the critical current density, there were some various parameters which I had to consider, such as A and B were the transverse dimensions where B has to be greater than A, and delta M is the magnetic differences from the image loops which were obtained from the squid magnetometer. Whereas after doing the following calculations, I was able to get the following data into critical current density data, which were plotted, and from this it shows that the JC values at 20 Kelvin applied magnetic fields were approximately 221 kiloamps per centimeter square at 0.5 Tesla. And it is also noted that the 4% addition was somewhat optimal compared to other scenarios, since it had 30% higher than the AG-free materials, around up to 1.5 Tesla. So in order to find a perfect model for my critical current density, I had used the models developed by Jirsa et al., a prominent scientist, and I had used this model which he had developed. So basically, A1 is the magnetization at the self field. So basically, it is the height of the peak, and minus B is the applied magnetic field, and B0 is the parameter which I had to vary in order to find a perfect fit for the model. And this is somewhat a decay model for MgB2 materials. And y'all will be wondering why it will be having a decay model, and you can also see that it fits perfectly, but it is just this area. So the main reason is that when we are modeling MgB2 materials, we will have to consider the core vortex size along with its coherence length. So therefore, this is a model which I had developed. The perfect fit for a silver-free MgB2 material was this equation, where this is the height of the peak, and minus B was the applied magnetic field, over where 8,100 is the parameter which I had varied, and where this was utilized for perfect fit. And this is another model for my thermal activated flux motion for 4% addition of silver, where this was the perfect model which I had developed. And so it was 380,000 times minus b divided by 7,600, where I had to again modify the parameters for finding the perfect fit. And now, before I go further into my modeling of GD123, I'd like to somewhat talk about the new enhancements of the transportation sector by GD123. And so basically in Japan, it had first started out with, this is the very first model that was developed. It's called ML100, and it is displayed in front of RTRI. And when it was first developed, the maximum speed it could travel was 60 kilometers per hour, and its weight was 3.5 tons. And the seating capacity was only 4 people. And now our Japan's future aim, and I think it will be further developed, was creating a maglev train by the company of GR Tokai. And its main aim is to develop a maglev train which can be traveling from Tokyo to Nagoya to Osaka in those directions by the year of 2025. So this is like another brief research of mine which I had published in the European Journal of Physics. And I have developed a prototype superconductor, and these were the necessary materials, and the following dimensions were given below in order to create the following prototype. So by using the following materials, I was able to create a prototype maglev rail along with a maglev prototype. So this is a somewhat applicable experimentation, since I had to find the optimum gap between the train track and the rail. And this is very applicable to the real life situations in the development of maglev trains. Therefore, I had varied the gap between the train and the track in several increments, such as I have done tests for 1 millimeter, 2 millimeter, 3 millimeter, and 5 millimeters. And from this test, I have figured out that 5 millimeter was the optimal gap, and I'll be discussing the reasons for this scientific experimentation. So from 1 millimeters to 3 millimeters, the gap was very small. Therefore, there was some applied force and applied friction between the train track and the rail. Therefore, the train could not run properly, and it did not have proper stability. So therefore, it could not run properly on the train track. And if I totally increase the gap between the train track and the rail, such as 10 millimeters and 15 millimeters, you can see from this qualitative results that the speed was very poor and the stability was extremely poor because the gap was way too big. Therefore, the train could not run properly on a train track. Due to this reasoning, 5 millimeter was the optimal gap, and this is the quantitative results. And you can see that 5 millimeter was the optimal gap compared to all other gaps, since it has one of the fastest speed, and along with that, its stability was also very nice. So it is very safe for current applications. But if the gap was very small, such as 1 to 3 millimeters or 7 to 15 millimeters, the train cannot function properly on the train track. Therefore, from this experimentation, 5 millimeter was the optimal gap. And further, I had also done further research after creating a proper prototype. I had also developed a model which perfectly fits for the critical current density for GD123 materials. It is somewhat, so modeling for GD123 materials, I had done the same processes for sample preparation and by using the split magnetometer, but modeling scenario was somewhat different. Since for MG123, it was a nice exponential decay, and I had just used one equation. But for GD123, you can see that I had to consider 2 additional curves for the perfect fitting for a GD123. Therefore, I had to consider the first equation plus this new equation, where A2 is the height of the second peak, and N will be the slope at which is decreasing. So these were the new parameters which I had to consider to develop a perfect model for GD123 materials. And from this graph, you can note that N was a very